Moving on now to take a look at the rear of a camera. You'll notice that here there's not a lot of optical stuff that's going on that's interesting, but instead you can see that there's a lot of circuit boards and a lot of computer-looking type devices that are inside of a digital camera that help us produce the image that we can. And every manufacturer has their own set of chips, basically, and algorithms that they use within it. In this case, you can see that Canon has highlighted their own proprietary chip called Digic, which is their sort of processing chip that they love to market all over the place. But this technology is really what helps us process, or rather what helps the camera process the photos and save them to your memory card, which is over here, as quickly as it does. And in fact, to give you an idea, for those of you that are familiar with computers, or rather some computer terms, so this is a 20D. This is a camera from 2004, so it is now 5 years old, and it can take 8 megapixel photos, which may or may not sound impressive, at a rate of about 5 frames per second. And so if you do the math, you figure out that that means that this camera can actually process about 60 megabytes per second of data. Let's see, so that's about 1/10 of a CD, for example, if you want an analogy. But nowadays, and so right now, the Canon world is sort of a flutter with a camera that Canon is rumored to come out with, or rather to announce tomorrow. And so I don't have any special knowledge about this except what I read late at night on Canon rumor sites. But it's supposed to be this super big, super fancy camera that is going to be very, very fast. And if we are to believe the rumored specs, it is going to be 18 megapixels at 8 frames a second, which is a significant upgrade. And in fact, that, rather than being about 60 megabytes per second in this 5-year-old camera, that is now 240 megabytes per second in 2009 form. So this tells us a couple of things. So unlike film cameras, digital cameras are now advancing at a rate that is similar to computers. So if you've ever bought a computer, go back to Best Buy or the Apple Store the next day and find out that it's been upgraded or made cheaper or something like that. The same thing is happening now with camera bodies. So if you're going to buy a digital camera, I'm going to say this several times today, really to hammer the point home, don't waste all your money on the camera itself. Instead, focus your money on lenses, because lenses do not depreciate in value. They do not change as frequently as the bodies do these days. So buying lenses is more of an investment than buying camera bodies. And in fact, for the most part, I recommend buying used cameras, because this is a 5-year-old camera, but it has better quality than a lot of the compact digital cameras out there today. And it's still very useful. It's still quick. 5 frames per second is not slow by any measure. And you can still get high quality used cameras at a reduced price. So don't waste your money buying new cameras unless you know you love digital photography and you have budgeted a certain amount of money, and I mean significant amounts of money, to purchase new camera bodies as soon as they are released. I've been waiting 5 years for a replacement for this camera, and if this rumored one comes true, it will be interesting. But I know that I love this stuff and that I've saved money, squirreled money away elsewhere to buy a new camera body, but otherwise using a used camera body is more than enough. Okay, so that's 2009. That's supposed to be a pretty good camera, and I'll certainly tell you in a couple of weeks if that has come true or not. But we should take a look back at where digital cameras actually came from. So 5 years ago, it sounds not as impressive as some of the stuff that's coming out today in 2009. But what about back, how about almost 35 years ago in 1975, when the first digital camera was born by Eastman Kodak engineer Steven Sasson. So again, this was back in 1975. And it looks like this, which is a little bit bigger than what we are used to today, even by SLR standards. It weighed 9 pounds. It was black and white. And it was 0.01 megapixels. So it took an image that was 100 pixels wide by 100 pixels tall. And that's tiny. That's very small compared to even camera phones today, which have several megapixels in size. So the iPhone, for example, has like a 3 megapixel camera or something like that, which is orders of magnitude larger. Oh, and also one final thing, it took 23 seconds to take a photo with this original camera. So we've obviously come a long way, and again, this is really to hammer the point home that digital cameras these days are more like computers than they were like film cameras of the old days. So don't waste all your money on that stuff. Okay, so moving on, back in 1983, Canon started looking at some interesting designs for digital cameras, thinking, oh, you know, this is going to revolutionize photography. It's really going to change the way we look and use cameras. I don't know if that's what they actually said, but I could imagine some marketer saying that. And they hired some designer, Luigi Colani, to design some SLRs, and this is what he came up with. So some very oceanic, very fishy, literally, designs for these cameras. And they're pretty cool, but I would not want to be walking around taking photos with something like that, looks like that. That is really, really horrible. And so eventually they started realizing that it was sort of silly, and that really the design that they've been using literally for years, if you notice that film camera, it's very, very similar in design to even the modern ones. Now they're a little bit, you know, more rounded and smoother, but for the most part, the general design hasn't really changed. That's a pretty good thing, and they're sticking with that. Okay, so this is some fun stuff, but this is a digital photography class, and so for us to really get into some of the nitty and gritty, we do have to talk about a little bit of math stuff. And being a computer science class, that means that we're going to reference bits and bytes. And so we are actually going to be using some of this stuff, maybe not today, maybe not 2 weeks from now, because we don't have class next week, but in a few weeks, we are really going to be talking about bits, bytes, a lot of these other things. So if you've taken some other computer science classes, hopefully this stuff looks familiar to you. A bit is the most basic unit on a computer. It's either a 0 or a 1, off or on, you can think of it. And so a byte is just 8 bits. So it's basically 8 zeros, 8 ones, or any combination of 8 bits that exist there. And so if we think for a second, so a bit represents 2 different values, right? So it's either a 0 or a 1. It's 2 different values. So if we have a byte, which is 8 bits, that means we have a bit here, a bit here, a bit here, so on and so forth, 8 times. That means that we have 8 slots for 2 units. So if you do, 2 to the 8th power, you can figure out that that means that 1 byte can represent 256 distinct values. So from 0 all the way to 255. Don't worry if that isn't review. It's useful to know that, and more than just for this class. If you use a computer, which I'm sure you do, knowing this stuff is actually pretty useful. And you can actually convert from binary values to decimals. So if we wanted to write 8 ones and call that a binary number and convert it to decimal, we could. But I'll spare you that math. That's not something that we need to do today. But before we have, not before we have bits or bytes, but before the word bit or byte, we usually have prefixes that denote some additional value. So we have some of the most common ones are kilo, mega, and giga. And so you'll notice that a kilobyte, for example, is 1,024 bytes. And the reason that it is not 1,000, that it is not just an even number, is because it is meant to be a power of 2. And it just so happens that 2 to the power of 10 equals 1,024. So it all works out sort of nice, and so just so long as you just have to remember that. So once you remember that part, then the megabytes is easy because it's just 1,024 kilobytes. So to figure out how many bytes that is, you have to do 1,024 times 1,024, and you get 1,048,576 bytes. You don't have to memorize how many bytes it is, but it's useful to remember the prefixes and to know that kilo is approximately 1,000 bytes, that mega is approximately 1,000,000 bytes, that giga is approximately 1,000,000,000 bytes. And this is the same sort of measurements that go into your computer hard drive, into even the memory card that we use for our digital cameras. We are talking about this same sort of thing. And so we actually use these fundamental values to represent digital photos. So this digital photo from earlier is made up of millions of little tiny pixels. As you can see, there's little square dots here that themselves in computer memory are represented by a series of ones and zeros. And in fact, we usually consider color to be separated into three constituent parts on a computer: a red part, a green part, and a blue part. So for every pixel that you see, and in this blown up version you can see there's one pixel here, one pixel there, so on and so forth. Each one of these pixels has three constituent parts: the red, the green, and the blue. And each of those is made up by 8 bits. So the red portion of that one pixel is given 8 bits of information. The green portion of that pixel is made up by 8 bits of information. The blue portion, 8 bits of information. And so you may say, well, I don't really see any green in any of these pixels here. That's just because that part is given a value of 0, for example, if there's actually no green in there. So we can think of each of these, and we'll talk in more detail about this, especially in the color lecture, but we can think of these as having values from 0, where there's the complete absence of that color, all the way to 255, where that is the complete presence of this color. So you can imagine that various combinations of these actually give us the colors that we see on the computer. And this makes up a very popular format that you'll probably recognize called the JPEG format. And so each one of these pixels is made up with 8 bits of information. And so you can then imagine if you're using a computer, actually, especially a Windows computer, and it's asking you the color depth, how many colors you want to display on the screen. Sometimes it says something like 8-bit color or 16-bit color or 24-bit color. When they say 24-bit color, they mean this. They're adding 8-bit plus 8 plus 8-bit plus 8-bit. So every pixel has 24 bits of color information, basically, if that makes sense. But it's not really important to us as digital photographers. This is more important, but I'm just trying to bring that idea back to something that may make, or that you may have recognized from home. So there's additional file types as well. There's also 16-bit file types. And for the most part, you won't really be working with 16-bit files, but it is very useful to know because most cameras are capable of producing more than just 8-bit color. This camera, for example, being 5 years old, is capable of 12-bit color. New cameras can do 14-bit color. And that may not sound like very much. You may say, oh, that's just 1 bit. Who cares? It's just 1 bit of information. But remember that 1 bit is either a 1 or a 0. So every time you add an additional bit, you are doubling the number of values that exist. So if you remember, I mentioned that 8 bits of information are 256 discrete values. But if you also remember, I said that 10 bits is 1024. So just by adding 2 additional bits, we've gotten a lot more bits of information. So the jump from 8-bit to 16-bit is a lot bigger than it actually sounds at first glance. This is actually, rather than 256 discrete values, this is 65,536 per color channel. So there's a lot more values, a lot more very subtle differences in the color for us to work with. And this is useful for us as photographers when we want to get the absolute most, the best amount of quality that we can possibly get out of a photograph. We will try to use these higher bit rates, 16-bit and 8-bit. And when we're representing these photos in a file, recognize that we are just saying that it's basically a table or a matrix, or however you want to think of it, of rows and columns of these pixels, each of which has 24 bits worth of information. And if you do the math, that is a huge file. It's very, very big, and so we have to figure out some way of compressing this information, of making it smaller so that our computers, our cameras, and even our email clients can work with this information and be able to send it and manipulate it in a much more easy way. And so there are various methods of compression, and one of the simplest ways is if we have something like these 2 flags. So, and let's assume for a moment that how we're going to compress this is we will look at each row individually in this. So we look at the very top row of this flag. Notice that it's the first color at the left side is black. And then we compare all the subsequent pixels after that first color, and if they're the same, then we just compress it. We say that that pixel is the same as the first one. So we say, okay, this first pixel in the very top of this flag is black, and so are all the subsequent ones on this row. So we can just say that in a file, and it's much smaller, it's much more compressed, and much easier to say and for a computer to understand than if we were to uniquely say, okay, this one is black, this one is black, this one is black, so on and so forth. Now, if we were to take a look at the French flag, this makes it a little bit more difficult, because as soon as we get about a third of the way through, we change colors. But still, we can still compress it quite a bit. Maybe not as much as this one, where we can go an entire row without having to change colors. But here we can go a third of the way without having to change colors, and then another third of the way without having to change colors, so on and so forth. We can compress the size of this file by a considerable amount. But there's a slight problem with using this compression technique in photographs, and what might that be? Yes? That's right. Yeah, very few photographs have such uniform color. Even in this photograph, you'd be hard-pressed to find two photographs in a row that match each other. So it's not going to work so well unless you have sections of color that are very, very uniform. So in this case, there's a photo of an apple. The background is perfectly blue, and we're able to compress that out. But the apple itself, because there's small changes in the gradient from black to red and to orange and so on and so forth, we can't actually compress this very well. And so if you're familiar with the GIF format, which you probably are if you remember Dancing Hamsters from back in the day, those were all animated GIFs. This is what the GIF format uses. And this is just one reason why the GIF format is not very well suited to us as photographers. And so instead, what we usually see are JPEGs, which compress things slightly differently. And so without getting into a lot of the technical details, it basically breaks apart the photo into a lot of different blocks. And then it looks at each block and it tries to figure out how it can simplify that mathematically. And so you'll notice that here on the left side, it's both of these are extreme zoom-ins from the face of this guy up here. And you can see individual pixels on the left side, but after some extreme JPEG compression, what you'll notice is that there's these sort of ugly big blocks that look uniform within themselves, but are not uniform with adjacent blocks. And this is part of the problem with overcompressing your images. By using JPEG, you're actually using something called lossy compression. And what this means is that it is actually throwing away some data that it thinks is not important. So the degree to which is defined by that sort of quality slider, if you've ever saved a JPEG and it goes from like 0 to 100 or something like that, the lower that value, the more bits it's going to throw out, and the more likely it's going to look like this. So you can actually save a JPEG that's very, very high quality, that won't have a lot of artifacts like this, but as a result, it will be slightly bigger. But because it is a lossy compression format, the more you compress it, the worse it's going to look. And in fact, I'm going to recommend that if you have a camera that takes JPEG photos, once you download those photos onto your computer, I recommend you save those originals somewhere, because at no other point in time in your editing of those photos or in your manipulation of them or whatever, will they be as high quality or have as many bits as they do right then. As soon as you open that file in Photoshop or iPhoto or any number of things, perform a change and save it, it's redoing this lossy compression. And every time you save a file that is lossy compressed, you lose a little bit more data, a little bit more data. So you want to be sure that you keep those original files so that you can go back to them if you need to and have the original highest quality format, or have the highest quality file that you possibly can out of your camera. Yes?
Does that apply even if you do sort of a save as and name it as a new file completely? Do you still lose?
Yes and no. So if you do a save as, doing just the save is extremely dangerous, because now you have absolutely lost that original data. You've saved over that original file, and it's a lossy compression format, so you're going to lose a few bits. But if you do a save as, then the original file that it was opened from is still unmodified. The save as file might have a little bit less quality. You may not notice it, but because it is a lossy compression, if you do it enough times, if you do a save as and then open that save as and then save as again and just keep looping over and over and over again, eventually you will see this sort of thing happen. Oh, that reminds me, there's this really cool internet video where this guy did that with a photo of the sky, basically, and he just kept doing a save and a save and a save in JPEG, and it was basically like a time-lapse video of the original quality of this photo until it progressed to be, you know, this horrible mess. And it was just a lot of fun to see. It really didn't take, well, relatively that many saves. It was something like 400 or something like that, but still, it's enough that it's, I know, it's silly, but still, it was enough that you could tell the change, and it was quite drastic. Yes.
Does that happen like no matter what, no matter how you're transferring the photograph, like even if you're copying and pasting it?
No, it does not happen. No, it does not happen all the time. Only if you resave the file as a JPEG. If you copy the file straight, so like right now I have some photos on this memory card, for example. Let's say I download them onto my computer. It's not resaving the file, so no compression is taking place. It's just copying the bits exactly as they were on this memory card onto my computer. So in that case, you can just copy the files without really worrying about it at all. It's really only when you resave the file that you have to worry about it, if that makes sense.
So when you say resave, it means when you change the format, save it as a format.
Yeah, even if you don't change the format, if you have a JPEG file and you go to File, Save As, or File, Save, for example, then it's going to resave those bits. It's going to recompress. So when it opens this photo, it has to decompress it to show it to you on your screen. But when you save it again and then it recompresses the file and saves it on your computer, that's when you get into trouble. I think I saw a question over here.
So is that an argument then for shooting everything in RAW and just
Yes.
using that as your starting?
That is an argument for shooting everything in RAW, because RAW file formats are losslessly compressed. They do not deteriorate. You have the original file. But there's a variety of problems with that as well that we will, of course, touch upon in the class. Yes? Oh, okay. Any other questions? Okay, great. Let us take a quick 5-minute break before we keep talking more file formats.